Hey, welcome back. We're talking about 7.5 today. We've been talking about normal distributions for a long time now. That's not the only kind of distribution. There's actually a lot of different distributions. Well, t-distribution's one example of a different kind of one, but we want to take one look at a distribution that's very different, just to give you a taste for what that looks like. And it's a distribution that we use when we're making a claim about the standard deviation or the variance. So that's how you're going to identify these problems. Is the claim will say something about the standard deviation or variance instead of the mean or the population proportion. This distribution is called the chi-squared distribution. And the notation for that chi is a Greek letter. We use a capital chi, which it looks like an X, only it's kind of curly on one end. So it's the chi-squared. That's how we designate it. And it looks kind of like this. Instead of being symmetric, it's actually skewed right. It's high on the left and then has a longer tail out the right. In addition, all of these values down here are positive. So they're going to start at 0 and go on up. So there's no, whereas the standard normal curve has 0 in the middle and goes negative and positive, this distribution does not. So the problems are very similar. The biggest difference is that there's not a p-value for these. So you actually have to use the rejection region method, which is the whole reason we introduced it in the first place, is because we knew this was coming. And so what you're going to do is you're going to find your standardized test statistic for your alpha, and you're going to compare you're going to find your critical value for your alpha and then compare that with your standardized test statistic from your sample. So let's jump into an example and we'll give it a run. So tire manufacturer claims that, here's your keyword here, the variance. So the claim is about the variance. That's my key, that I'm a 7.5 problem doing a chi-squared distribution. The variances of the diameters in a certain time model is 8.6. So is means equals. So we're going to do variance. Let's remember what the notation is. This is the population standard deviation, and this is the population variance. So these are the two labels that you're going to be using for your hypotheses tests. So since it's variance, we're going to do sigma squared. Is means equals 8.6. So that's going to be your claim. The complement of that is sigma squared is not equal to 8.6. H naught is the equal sign. HA is the one that's not. And HA dictates what kind of a tail test we have. So even though it's not symmetric, we still can have a left, a right, a two tail, works the same. The only difference is these values, where in the Z distribution, in a normal distribution, when we have a two-tail test, these critical values are equal with just opposite signs. That's not going to be true this time. So you can't just take one and label it on the other. We actually have to find both independently. So we're going to find this critical value, my chi-squared critical, and here, whoops. Lost the whole deal. Chi-squared critical. We have to find both of those associated with our alpha. So let's figure out what our alpha is. It's 0.01. So because this is a two-tailed test, we're going to divide that in half. So we've got an alpha value of 0.00. Oops. 0.005 on each side. So that's just my alpha divided in half on either side. And now we're going to find the critical values. I'm going to do class calc first. It's a little bit easier. So to find our critical values associated with alpha, we're going to go to stats, and we're doing distributions and plots. Remember, this is our inverse CDF situation, right? We have an area, we want to find the value for it. So it works the same way. This is what you do for a Z distribution. This is what you do for a T distribution. And look below it, this is our chi-squared distribution. So I'm going to tap on that. And it's asking me again for degrees of freedom, which is what we talked about with the T distribution. The chi-squared are the same way. The sample size dictates the shape of this curve. And so I'm going to go back to my problem, figure out what my sample size is. Looks like I have 10 tires as my sample. So my degrees of freedom are going to be 9. It's always one less than your sample size. And again, if you remember, you hit this magnifying glass right here, and it'll kind of center your graph. So you can see how this is a chi-squared. It's skewed to the right. It's got a long tail on the right. It's not symmetric. And so we are going to find our critical values associated with our 0.005. So we do it the same way we have with all the other problems. Go under stat and under distribution plot, and we're going to tack on this dot inverse CDF to the end of it. And you're going to put your area in at 0.005. And I get 1.73. So that's going to be this 1.73. Now, how did I know it's that one? I'll show you. Okay. When you find the other one, I'll show you the trick to it. Let's talk about the second one though. Remember, inverse CDF always measures from the left. So I entered 0.005 and I got this distance there. But now I have to figure out what this distance is here to get this critical point right there. Okay, so let's do a little subtraction. I'm going to go, first of all, I'm going to take, well, let's just do this. I'm going to go 1 minus 0.005. That's going to be my green section. So if my yellow section is 0.005, then the green is going to be 1 minus that. Okay. So 1 minus that is going to be 0.995. So I'm going to go over to my calculator now, and I'm going to enter 0.995. And I get 23 point, let's call that 23.59. So this is going to be 23.59. Now it starts on the left at 0 and goes up from there. So the way you figure out which one's which is you just find both, and the small one goes on the left and the big one goes on the right. Okay. If you ever get confused. Okay, so these work exactly the same way as your normal distribution. You're just using a different button on the calculator. So these are your critical values, and your rejection region is going to be, because this is a two-tail claim, let me shade this a little differently. My rejection region is going to be in the yellow. So in either tail is going to be my reject H naught region. So what I would write is chi-squared can be less than 1.75, or chi-squared can be greater than 23.59. That this is going to be my rejection region. Okay. Now let's talk about class calc, or TI. Okay. Here's the problem with TIs. They don't have this chi-squared distribution option. So if you're using a TI, you're going to need to use a chart for this section. Okay, so here's what the chart looks like. If you have a book online, you can look at your book. In the back, in the appendix, it has all the charts. And this one's here. It's called the chi-squared chart. You can screenshot this if you want. They also have this as a handout in the Math Center if you want a hard copy of it. Okay. I will give this to you on the test day. The confusing thing about the chart is that it's the only thing in this class that measures from the right. You know how we've been doing inverse norm always from the left? This one goes from the right, and I don't know why it does that, okay? So I apologize, but you need to remember that. So I have my chi-squared distribution here. I have a two-tailed test, and I've got 0.005 on both sides of it. So because this measures from the right over, when I look up an alpha value of 0.005, I'm getting that right-hand limit now. So it's backwards from the inverse norm. So I'm going to look up here at my alpha. I'm going to find 0.005 right here. And then I want to look for my degrees of freedom, which is one less than my sample size. And I think we said our sample size was 10. Let me just confirm that. Yeah, 10 tires. So our degrees of freedom is going to be 9 right here. So I go over and I find where they intersect, right, like that. And I get 23.589. So if you want to go back here, 23, oh, we rounded. Okay, we rounded differently, but this is 23.589. Okay, so that's that guy. And then how do you find the other one? Well, you're going to go 1 minus 0.005 to find your left one. So that's going to be an alpha value of 0.995 and come down here to 9 degrees of freedom, and you get 1.735 for your other one. Okay, so that's how my TI people are going to find their critical values. All right. After we find our critical values, we're ready to run the hypothesis test. And the other difference between a chi-squared and the others is that neither calculator actually has a hypothesis test for chi-squared. So we have to do this by hand. So there's a formula, okay? The formula is that chi-squared, this is going to be your standardized test statistic. And so this is the value that we're finding based on our sample that we're going to compare to our critical value. So the formula is going to be n minus 1 times my sample variance divided by my population variance. Okay, so let's go plug those values in. My n minus 1, I know, is going to be 10 minus 1, because that's my sample size. My sample variance is the variance from this sample of 10 tires. So a random sample of 10 tires has a variance of 4.3. So that's going to be 4.3. And then my population variance is going to be what my claim was about. So it's very similar to when we were entering on the calculator, and it would ask you for that sample statistic, and you'd enter that from your sample, and then the population statistic would be from your claim. It's the same idea. So this is going to be 8.6. All right, once we get this, I'm going to calculate this out. I've got 9 times 4.3, and then I'm going to divide that by 8.6, and I get 4 equals 4.5. Whoop. I've got a line across my calculator, so I just need to check and make sure I was reading that right. Yeah, 4.5. Okay. So this is my standardized test statistic. So that's going to be, let's go see where that is on the graph. Let's put that in this blue, 4.5. So if this is 1.7, this is 23, 4.5 is about here. So that's in the inside of the curve. So this is going to be a fail to reject H naught. So if it was in the yellow region, then you would reject H naught. But if it's in the inside of the graph, we're going to fail to reject H naught. All right, let's take a look at our chart. We're failing to reject H naught. Our claim is H naught right here. So there's not enough evidence to reject the claim. Which makes sense, right? If H naught's the claim and we fail to reject it, then we don't have enough evidence to reject it. That makes sense. And that's how you do these, okay? So the biggest difference is, I mean, for my class calc people, the only difference is that you're doing this part on a formula. For my TI, the difference is this, and that you're looking up these values on the chart instead of using your calculator. Okay, these problems can also be done with data, and I want to run through one of those with you. So let's do this guy. So this is talking about annual salaries of 14 firefighters. And we want to know about this claim that the standard deviation of these salaries is different from 5,500. Different means not equal to. So this is going to be a two-tail again. But this time we're talking about standard deviation. So my notation is going to be sigma now instead of sigma squared. So this is my claim. The complement of this is equal to. My HA is going to be my equal to, or excuse me, whoa, my H naught is going to be equal to. My HA is going to be not equal to. This is going to be a two-tail test right here and right here. These are going to be my alpha values. Alpha is 0.05. So I'm going to divide that in half and I get 0.025 on each tail. Now, if this is a one-tail test, you don't divide in half. It all goes in the one, either the left or the right, okay? The bigger number is always going to be on the right, the smaller on the left. So that's how you tell which is which. So for my TI people, we're going to be looking up, let's see, we have a data points. We have 14 data points. So my degrees of freedom are going to be 13. And I'm looking up 0.025 and 1 minus 0.025. This one's going to be 0.025 and this one is going to be 0.1 minus 0.025. But if you get confused, you just put the smaller one on the left, the bigger one on the right. So let's look those up. If alpha is 0.025 and my degrees of freedom are 13. So this is going to be 24. Let's call that 24.74. And then 1 minus 0.025 is 0.975. So that comes down and we're looking at, let's call it 5.0. Those are my critical values. Critical values. For my class calc people, we're coming over here. We are doing stat distribution plot. We are doing a chi distribution. Our degrees of freedom are 13. Then I'm going to go back into stat distribution plot and do my inverse CDF. And I'm doing 0.025. That's going to give me the 5 value that we just saw. And then I'm going to do 0.975, and that's going to give me my 24.74. Okay. All right. Next thing is to figure out this test statistic for my sample. So my formula, chi-squared, is going to be n minus 1 sample variance over population variance. Now, in this situation, I don't have the variance. I have the standard deviation. And the standard deviation is just the variance, but not squared. So when you go to plug this 550 in for your population down here, you actually have to square it this time, because this is just sigma and we want sigma squared. Now, when it was the variance, it was already squared, so we didn't have to square it again, okay? So that's something that you need to pay attention to. Standard deviation, square the number. Variance, don't square it. My n minus 1 is 13. And now I need my sample. Whoa, just kidding. Thought I had my pencil on. My sample variance. Now, how do I do that? Way back, think back to chapter 2, when we just took raw data and we found all of the measures of spread and center. Okay, how did we do that? We went into our calculator, we entered a list, which you see I've done here. Here's my list A with all of my data points in. If you're a TI, you're going to hit stat and edit and put your numbers in your L1 like we've done before. And then when I come down here to my second row, I'm going to go advanced. Actually, wait. Oh, sorry. In class calc, it's under basic. And I just want the variance right here. So I'm going to hit that. And I want the variance of list A. And it's going to give me that. The sample variance is this. Now let's talk about this number. This is 6.05 times 10 to the 7th. That means that you're going to take this number and you're going to move the decimal place 7 to the right. This is scientific notation. So what I'm going to do is I'm going to take this number that we have and move the decimal 1, 2, 3, 4, 5, 6, 7 to the right. Okay, that's the variance. Now that's the variance, so it's already squared. Okay, if you want to square the number yourself, you can do that, but then you're picking up, then what you're going to do is you're coming down here and you're going to do the standard deviation of A. And that's going to be this 7780. And you're going to square that number and you'll get the number that I just wrote over there. Okay. So it doesn't matter how you do it, but just keep in your brain, if you wrote down variance, you don't have to square it again. If you wrote down standard deviation, you do. For my TI people, you're doing stat, you're doing edit, and you're entering your numbers into list 1. Then you're going to go under stat and you're going to go calculate, and it's 1 var stat. And what you're looking for is either it's SX on your calculator. That's going to be your standard deviation, sample standard deviation. And then you're going to square that number to get your variance. So either way, both of you guys have to pull this number off your calculator and then you just crank this out. So I'm going to go 13 times 605 30700. And I'm going to divide that by 5500 squared. And I get 26.01. Okay. So where is that? Here's 5. Here's 24. So 26.01 is up here, and that is in my rejection region. So that means that I'm going to reject H naught. So I'm rejecting H naught. HA is the claim. Oops, sorry, wrong way, making you dizzy. So I'm rejecting H naught. HA is the claim, so there is enough evidence to support the claim. All right. So if you think about it logically, my claim is HA. I reject the opposite of the claim. Well, if the opposite's not true, then the claim must be true. So there is enough evidence to support the claim. I always like to think through that and make sure I wrote down my sentence correctly, because if it doesn't make sense, then you might have copied it down wrong. So that's it for the chi-squared distributions. We will talk more next time.